All right. Hi, guys. So we're going to go through exponential, kind of an introduction to exponential and logarithmic functions today. So make sure you have out your notes, and we're actually going to start on the second page that says exponential growth and decay. This is something that you saw back in Math 3, okay? Exponential growth, the formula for that is y equals a 1 plus r to the t, and then decay, a1 minus r to the t. So that's how you tell whether it's growth or decay, by looking at whether it's 1 plus or 1 minus. All right, so we're going to do two examples here. Notice that r is the rate as a decimal, so that's important. So Brooke starts with 32,000. That's my initial value. Each year her salary increased, meaning this is growth, by 2.5%, but I needed to turn that into a decimal. So I'm going to move my decimal place 2 to the left to get 0.025. And we want to find her salary when she retires in 30 years. So that is my t, so I'm going to raise it to the 30th power. When you type that all in your calculator, you get $67,122.16. I round to 2 decimal places there because it's money. So money, 2 decimal places. If it's like talking about people or animals or something like that, we're going to round to the nearest whole number because we don't want to kill people. All right, number 4. The half-life of mercury 197 is 3 days. All right, so we start with 50 grams. That's my initial value. Half-life means it's decaying by half, okay? So 1 minus 0.5, or you could just write that as 0.5. Now, it only decays by half every 3 days. So I'm going to write that as x over 3, or t over 3, where that's my time. And then we want to find how much is left after 20 days. So I'm going to plug in 20 for t and type that all in my calculator, and I get 0.492 grams. All right, going to the next page, we have something called continuous growth and decay. This may be new. My formula for this is called Pert, P-E to the RT, where R and T are in the exponent. P is the initial value. E is actually an irrational number, okay? It's just like pi. If you type it in your calculator, you can actually get to it on your calculator by hitting second divide, and that will bring you to E. So you can see in just a second when my calculator loads up that if I hit second divide, that's E, and it's about 2.718. Okay. All right. So that is that. So anytime you see the word continuously, we're going to use the Pert formula. If we don't see that, then we'll just use our normal growth and decay, 1 plus R, 1 minus R. So we start with 4 pounds of garbage, and it increases continuously by 35% each day. So 4E, and I really don't need those parentheses there, to the RT. So R being 0.35. And T, notice it's happening each day, and we want after 2 weeks. So that would be 14 days. All right. And then when we type that in our calculator, we get 537.159 pounds of garbage. The other type of function we're going to talk about is called the logistic growth function. You may have seen this before in maybe AP Environmental Science or something like that. It's where basically the function is growing almost exponentially, and then it starts to level off. This leveling point is called the carrying capacity. Make sure you write that down. You do need to know it. And you can see that in the equation by the number in the numerator. So that tells you what that function will level off at. It might also be called a limit to growth. So we can see we're increasing, and then it levels off at that point. So for example, in number 7, there's a town of 20,000 people. So I can see in my numerator, my carrying capacity is 20,000 people because that's the maximum that it could infect this disease. After T days, the number of people who have been infected by the disease is modeled by this function. Find the people infected after 10 days. So all that's saying is T equals 10, and we just need to plug that into our calculator. I like to usually do this in 2 steps just to make sure the fractions don't get confusing. So I'm going to do the denominator first, 1 plus 1150, and then remember to get E, second divide. And then in my exponent, negative 0.95 times 10. All right, so that's just the denominator, and then I want to do 20,000 divided by that, and don't round that until the end. So I get 18,414.86, and we're talking about people that are infected, so we're going to round that to the nearest whole number. So 18,415 people are infected after 10 days. Now, just to think about this, kind of again thinking critically about what's going on, if I wanted to find the initial number of people infected, or and this could be anything in context, initial value, anything like that, that's just going to be when t equals 0. So you would employ the same strategy there, just plugging in 0 for your time. All right, so then the next section is compound interest. You did see this in Math 3. So a equals p 1 plus r over n to the nt, where a is the final value or the future value. P is the principal or initial value. R is the rate, again as a decimal. N is the number of compounding periods per year. Okay, and T is your time. So in number 1, Dave invests $300 in an account, 5% interest. We want to find the balance after 15 years. So we start with 300. 1 plus, my rate is 5%, so 0.05, but it's happening semi-annually, which means 2 times per year. So I need to take that 5% and divide it by 2. I always say divide on the inside, multiply on the outside. So then in my exponent, I have n times t, so 15 times 2, or you could just go ahead and simplify that to 30. Again, I'm dividing by 2 inside the parentheses. I'm multiplying by 2 outside in my exponent because it's happening 2 times per year. When you type that in your calculator, you get $629.27. Again, rounding to 2 decimal places because this is money. Same thing for monthly, but this one is 12 times per year because 12 months in a year. So 300, 1 plus 0.05 over 12, and then 15 times 12. And I get 634.11. Notice that if everything stays the same, if you compound more frequently, you're going to end up with more money because you're making interest on your interest. I'm going to have you try numbers 2 and 3, but something to point out on number 3, this one says it's compounded bi-monthly. This has 2 different interpretations depending on who you ask. So I want you to go ahead and use that as 2 times per month. So think about if there were 12 months in a year and it happens twice a month, my n would equal 24. So bi-monthly could mean 2 times per month. It could mean every other month. We're going to use the definition 2 times per month, which should help you solve that. All right, lastly, let's do number 5, okay? And then we'll do a continuous one. All right, so Carter invests $1,000 and it earns 2 3/8. So if we think about 3/8 is 0.375, so that would be 2.375% for my annual interest rate. And then turning that into a decimal, I get 0.02375. Don't round that, just leave it exactly as it is. So we start with $1,000. 1 plus 0.02375 divided by 4 because this is compounded quarterly. And then we have to figure out, it doesn't give us a time, but it says from 1990 to 2025, that's a time period of 35 years. So 35 times 4 in my exponent. Again, divide on the inside, multiply on the outside. When you type that in your calculator, you get 2290.55. All right, and then the last thing is just continuous compound interest. This is the exact same as what we saw before. If we see continuously, we're going to use PERT, so PE to the RT. Just this time we're talking about money. So in number 6, $800, and it's compounded continuously. That tells me to use PERT, not the 1 plus R. So 800E, and then my rate is 6%, so 0.06. And my time is 20. So nothing has changed from how we did continuous before. Just if you see continuously, you use your PERT formula. Otherwise, the 1 plus R or 1 minus R. When you type that in your calculator, you get 2656.09. Again, rounding to 2 decimal places because this is money. So make sure you go back and try the ones that we haven't done yet, and then work on some extra practice either on Delta Math or on Canvas. So that kind of gives you an overview. A lot of that was review of exponential and logarithmic functions, mainly exponential, but